on uncertainty, beliefs, and probability. So what we're going to do is take some of these terms that we've kind of defined and refined a little bit, and we're going to get really precise about how we're going to use them in this course, okay? So we have to deal with uncertainty, all right? If things were certain, then rational behavior is easy to spot, all right? Someone walks over and picks off the tree their most preferred outcome. And the action was picking the thing off the tree, and they got their most preferred outcome. There's no uncertainty in that scenario, all right? But rarely can we know with certainty that an action will always lead to a certain outcome, all right? Even studying to try to get an A in the class, right? It doesn't always lead, the actions you take don't always lead to the outcome that you think it will because of all sorts of things. I could be an asshole and give a hard exam. Your roommate could be making a lot of noise while you're trying to study. There's a lot of other things in the world that make things uncertain, okay? So let's try to be as precise about beliefs as we are about preferences. Remember, we took preferences, a preference ordering like this, and we made it more precise by turning it into utility numbers, right? We said that maybe this person likes X with 1 util, they like Y. I think the example we had before was 0.2 utils, and person I didn't like Z at all, right? They thought Z gave them 0. So we're going to be just as precise about beliefs as we were about preferences, all right? So a belief is a probability statement. It says how likely is something to happen. If I do A, how likely is it that I'll get X? How likely is it that I'll get Y? Right? There can be multiple outcomes. That's what uncertainty means, right? You roll a dice, and that's the action, rolling the dice, and you could get any one of, I don't know, let's say roll a die. Let's do 1. You could get any number of 6 different outcomes, all right? And there's an equal probability of all of those. Well, in the real world, you might choose an action that has 3 different outcomes, but maybe the probabilities are not equal on those things. And so that's where we're going to go with this. So let me give an example, a kind of generic example first, and then we'll do one that's more specific. So person I has 3 actions that they can choose from. They can do action A, action B, or action C. There are 3 possible outcomes in this story. One outcome is X, they get X. One outcome is that they get Y, and one outcome is that they get Z, all right? So let's say that our chooser has a preference ordering where they prefer X to Y to Z. We still don't know how much more they prefer X to Y to Z, but that's going to be their preference ordering. So they have complete and transitive preferences, and therefore they have a preference ordering, all right? So let's now assign utility. And I'm going to say that they like X at a utility of 3, they like Y at a utility of 2, and they like Z at a utility of 1. Now notice, I can't get that directly from this. I know that this number should be bigger than this number, should be bigger than this number. I know that from the preference ordering, but I had to pick these specific numbers. And if you're constructing a model, you would have to pick them, numbers that you think are useful for your model. All right, but let's say that that's the utility person I gets for X, 2 is the utility they get for from outcome Y, and person I gets a utility of 1 for outcome Z. Okay, so you may want to write these down for future reference so you don't have to keep rewinding and coming back. All right, so now let's talk about their beliefs. All right, so action A leads to a 50-50 chance of outcome X or outcome Z. All right, so if I choose to do A, I might get X, I might get Z, and it's a coin toss. It's a 50-50, all right? If I choose to do action B, it's going to lead to a coin toss between outcome Y and outcome Z, all right? And if I choose to do action C, that will lead to an equal chance of each one of these outcomes. Right? So those are my beliefs about how effective these actions will be in getting these outcomes. I believe that if I do action A, there's a 50-50 chance of X or Z. Those are my beliefs. So we're going to take those beliefs and turn them into probability statements, sometimes called probability functions if we want to get fancy about it. All right? So let's rewrite these beliefs as probability functions. Okay? So let's see. I've got my notes here. So for action A, we're going to say that the probability that action A leads to outcome X, the probability that action A leads to outcome Y, and the probability that action A leads to outcome Z. All right? Equals. The same thing for action B. The probability that action B leads to outcome X, the probability that outcome B leads to that action B leads to outcome Y, and the probability that action B leads to outcome Z equals. And then for action C, the probability that action C leads to outcome X equals the probability action C leads to outcome Y equals, and the probability that action C leads to outcome Z equals. All right, so remember what we said before. The person believes that if they do action A, there's a 50-50 chance of getting X and Z. To consult my notes there. So the probability that action A leads to X is 1/2. The probability that action A leads to Z is 1/2. And the probability that action A leads to Y is actually 0. All right, so notice each probability outcome pairing has a probability statement. Even if it's 0, it's still there. And the other thing is it must add up to 1. If you do action A, something will happen, one of these three things. So the probabilities over here must add up to 1. All right. For action B, we said that the probability that action B led to outcome X was 0, and then it was a 50-50 chance of whether you get Y or Z if you choose action B. And again, notice each action outcome combination has a probability, even if it's 0, and if you add them all up, they sum to 1. All right. For C, we said there was an equal chance that if you do action C, that you might get any of the three. It's an equal chance. Notice each action outcome combination has a probability, and when you add them up, they sum to 1. Okay? So we've rewritten those beliefs as probability functions. Okay? And again, you may want to write these down now so that we can use them later on and you don't have to rewind and come back. All right? So as I showed you before, the probability numbers are all between 0 and 1, and they all must add up to 1. And I showed you that on the previous screen. Okay? And you may want to write them down. I had that in the notes for you. All right. So now, how do we think about agents making decisions when there is uncertainty? All right. Making a decision under uncertainty, under uncertain conditions, means choosing from different, we're going to call them lotteries. All right. So if I pick an action, there's some random chance that this happens, and there's some random chance that that happens. That's why we call it a lottery. All right. A rational choice is the one that chooses the best lottery, or the lottery for which there is no better lottery. All right. This is known as the principle of expected utility. We can assign a single number to each action lottery and then choose the one that has the largest number. All right. And that's what we're going to go through with this example step by step. All right. So we're going to calculate the expected utility of action A. All right. So the expected utility of action A looks like this. The expected utility of action A is the probability that action A leads to outcome X times my utility for X. All right. I value X this much, and this is the chance that if I choose action A, I will get X. So I multiply the probability times the utility. All right. Now, what is the probability that action A will lead to Y? Well, then I multiply that by how much I like Y. So the chance that I get Y if I do action A times how much I like it. The same thing for Z. The probability that action A leads to outcome Z times how much I like outcome Z. Okay? So similarly for B, the probability that action B leads to outcome X times the utility for X, the probability that action B leads to outcome Y times the utility for Y, and the probability that action B leads to outcome Z times the utility of Z. And the same exact thing for action C. All right. Once we calculate these, rationality requires the chooser to select the action that maximizes their expected utility. They want to pick the biggest number. Okay, so let's do each one of these, and we're going to start with the expected utility of action A. So here's that formula again. Probability that action A leads to X times the utility for X, yada, 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 all the way down. So first, let's fill in the utilities. And if you wrote those utilities down earlier, you'll remember that agent I, the utility that agent I gets for outcome X is 3. The utility that agent I gets for outcome Y is 2. And the utility that agent I gets for outcome Z is 1. All right. Now I'm going to go through and fill in those probabilities that we wrote down. So the probability that action A led to outcome X is 1/2. The probability that action A led to Y was 0. And the probability that action A led to Z was 1/2. So now I've got just a simple arithmetic. All right, 1/2 times 3 plus 0 times 2 plus 1/2 times 1. All right, and so that's 3/2 plus 0 plus 1/2. And then the expected utility of action A is 2. All right, let's do the same thing for action B. So first I'm going to come through and fill in the utilities. The utilities are the same. This person gets the same utility for X and the same utility for Y and the same utility for Z. It's how much they like it. So those numbers will be the same in each of the 3 utility calculations. What changes are the probabilities. How likely is it that this action, action B, will lead to outcome X? All right, and we wrote those down before, so I'm going to go ahead and fill them in. The probability that action B led to outcome X was 0. The probability that action B led to outcome Y was 1/2. And the probability that action B led to outcome Z was 1/2. Again, now all we're left with is just some arithmetic. So we get 0 plus 1 plus 1/2, and the expected utility of action B is 3/2. All right, moving on to C. The expected utility of C is the probability of action C times X times the utility for X, yada, yada, yada. You've got that now. The utilities are the same. Again, the expected utility calculation doesn't change how much they like those things. So those utilities have stayed the same. The thing that differs is how likely this action is to get me this outcome, to get me this utility, to get me this utility, right? So I'm going to fill in those probabilities we wrote down before. It was a 1/3, 1/3, 1/3 chance that action C would give you those different outcomes. And now, again, we're left with arithmetic. 3/3 plus 2/3 plus 1/3, and the expected utility of C is 2. Right? So what should this agent do? The expected utility of action A is 2. The expected utility of action B is 3/2. And the expected utility of action C is also 2. So a rational choice is a choice for which there is no better choice. These two are equal, so either one of these can be considered a rational choice because there is no better choice than action C, because action A is not better, it's the same. All right. So now let's go back to one of the earlier screencasts and think about William Weld. What if we wanted to do an expected utility calculation for Weld? So let me remind you of that story because it may have been a bit since you watched that screencast. William Weld was the governor of Massachusetts. He was trying to decide, did he want to run for governor or run for Senate? All right. There were 3 possible outcomes. If he could become a senator if he won the Senate race. He could become a governor if he won the governor's race. But if he lost the senator's race, he would be out of the political game for a while. All right. And we said that Weld had a preference ordering that he preferred to be senator more than being governor again, and he definitely preferred those two more than being out of politics altogether. So now I have to assign a utility number for each of these outcomes. And so for this story, it made sense to me that, well, being senator was his best, most preferred outcome. His second most preferred outcome is being governor, and those are probably pretty close to one another. But being out of politics is definitely a good bit worse than both of those. So I made a choice to make 3 utils, 2 utils, and then 0 utils. So there's a bigger difference between being out of politics and being governor, right, than being governor and senator. It's a bigger difference in his utility. All right. Okay, so what were William Weld's beliefs about this? Well, we said that if he ran for governor, it was almost all but certain that he would become governor again. And I'm sorry about these slides had some mistakes that I had to correct by hand here, but it shouldn't trip us up too much. 100% chance that he would become governor. All right. If he ran for Senate, all right, then there was a 50% chance that he would become a senator, and there was a 50% chance that he would be out of the game altogether. All right. So using this information on the last 2 slides, try to calculate the expected utility of William Weld's possible actions. All right. Maybe pause things and then you can move along. So let's do that expected utility calculation for running for Senate. All right. So it's the probability that running for Senate leads to becoming a senator times the utility of being a senator, the probability that running for senator leads to becoming governor times the utility for being governor, and the probability of running for Senate leading to being out of politics times the utility for being out of politics. All right. So I'm going to plug in those utility numbers, 3 for being a senator, 2 for being a governor, 0 for being out of politics, and then plug in the probabilities. The probability that if you run for a senator, you'll be a senator for William Weld was 1/2. The probability that if you run for senator, you'd be a governor is 0, because that doesn't make any sense. And the probability that if you run for senator, you're out of politics is 1/2. And we can do that arithmetic, 3/2 plus 0 plus 0. The expected utility of running for senator is 3/2. All right. What about running for governor? All right. So the probability that if you run for governor, you become, well, let's go ahead and fill in the utilities. They're the same. 3 for being a senator, 2 for being a governor, and let's say 0 here for being out of politics. And yeah, and so I got to correct it each time it pops up. So now I plug in those probabilities. There's no probability if you run for governor that you're going to be a senator. There's no probability that if you run for governor that you're going to be out of politics. But the probability if you run for governor that you'll be a governor is 1 probability. So this is just some arithmetic here. So we have 0 times 3 plus 1 times 2 plus 0 times 0. Remember, that's a typo there. That's actually 0. Maybe I should do this. There we go. Write out the 0 there. So those zeros all go away anyways. And so what we end up with is 0 plus 2 plus 0. And so the expected utility of running for governor is 2. And I'm just going to mark these out to make sure I get them on each slide. All right. So William Weld's rational choice was indeed to run for governor. Running for governor gave him 2 utils, and then what was it? Running for Senate would give him 3/2 of a util. 2 is bigger than 3/2. So that's 2 examples of how to do these expected utility calculations. All right.